All right. Hello, everybody, and welcome to this webinar, the second one in the series about the reinforcement learning in finance. From playing games to algorithmic trading. So we got started with playing games, admittedly a pretty simple game. So we haven't endeavored into the world of the Atari 2600 games, the paper about which I've mentioned in my introduction. And there have been already in the first webinar quite a few questions with regard to reinforcement learning, Q learning applied to finance and trading. And yeah, today we are going to make this step. So I want to do a review, and I also want to show an alternative implementation of the algorithm, not using Keras and TensorFlow, but simply, quote unquote, scikit-learn with the MLP regressor. This works as well, and it's sometimes a bit faster. Even we don't have all the flexibility that we have with TensorFlow. This works as well, and I want to use this as a review mechanism so that we go through another notebook, which is basically the same as the one that I used with Keras TensorFlow, but where we use simply another package. So you know that most of the code is based on AI in finance that I'm going to present, and the use case is algorithmic trading. That's the primary focus, to trade one instrument, so a trading bot that is able to go long and short, let's say with regard to one instrument, a stock or an FX cross or whatever. So that's the background that we have. And here you see the resources. I've added here an additional link. Apart from that, the slide deck is the same as last time, because it's a little bit more convenient. Maybe if you don't want to clone the repo, just to use the Google Colab link. I've added also like GitHub, Hilpish, my account there, RL Finance is the GitHub repository. So when you click that link, Google Colab opens, and then you can choose simply from the 4 notebooks. So I've checked them. They should all execute on Google Colab, but with a free tier, that's basically a little bit slow, actually. So I noticed that it's much slower than on my Mac M1. So currently I'm traveling. I'm doing this from my MacBook Air with the M1, but it's still as fast as my machine that I have back home with the M1. Yeah, in the cloud a little bit slower, but nevertheless it's kind of completely convenient. A single click and you are good to go. Discord server should be clear, and would be nice if you follow also on Twitter. Haven't been too active there, but more will come on Twitter as well. So I don't want to go through all the different things anymore. You might recall that success stories here, the basics we've covered first, the stories themselves, and then the Atari games, AlphaGo, which was a major breakthrough, then chess with AlphaZero later on, right? And we have then defined basic notions that we need, like environment, the state of an environment, agents taking actions in such environments, how we step forward an environment from one state to another state, a reward for chosen action, and a certain target should be clear. Again, in finance, this might be a profit or a large return, average return, compounded return, continuous return, whatever we want to define there. So this is more for later. The policy represents what an agent will do when the agent is in a certain state and has a certain set of options. An episode is simply one game or one trading period, right? And we have covered reinforcement, Q learning, reward function is important, and reward design is something, yeah, that is sometimes I think more an art than a science, right? To come up with a proper reward which lets the agent learn faster and then come up with better action policies. And the Q learning involves, yeah, delayed rewards, which is kind of the major characteristic. So looking forward into the future and not only having like the immediate reward. And I said, for us human beings, it's the same, right? When we have some sweet chocolate in front of us, we hardly can resist, right? You know, whether there is a punishment in the form of a pound more next week, this is usually not what we take into account then. But the machines behave similarly. Usually they are greedy, but we should teach them to also take into account future rewards. Representation, usually in the form of a deep neural network, right? This is what we choose here. The reason why, because deep neural networks are so good at approximation, at representation. And then we do exploration, exploitation, replay, to train, to update the agent. So this is everything that we have covered, right? And a few technical things, right? The discount factor, epsilon decay in this context, so the relationship between exploration and exploitation. So that's basically a quick run, but I said I want to review this based on code. So here I have used this to update the gist, and I dive now into this Jupyter notebook. So I said I have only my MacBook. Maybe here and there I might put on my glasses, or maybe I can simply zoom in a little bit more, right? So this notebook has basically the same structure and the same goal, the same approach as the one that we had with O2 here, Q-learning with Keras. And I just wanted to show that this also works with scikit-learn, where we have the MLP regressor, which we can use as a substitute. And I promised already this might be a little bit faster. So the card pool environment is not discussed here in detail, so I simply go with the first one, the V0, and I use, as pointed out here, the MLP regressor. So basically I don't need this will be defined. Further down, I said there is the block where I first kind of like years back, but still I'm referencing it because I found it so useful given all the other information that I had. This was like the best explanation that I found after a little bit of digging, so I still reference it here. So the structure above here is basically the same, so we wouldn't see any difference. I also called this DQL agent, where the major difference is to be found here is in the build model part, right? We now use MLP regressor and not like the sequential model of TensorFlow Keras. We have hidden layer sizes here, where number of hidden layers and number of hidden units. We can choose the optimizer. The learning rate here is fixed to constant, and we fix the random state so that we have quite some reproducibility. It's much more easy to come up with reproducible implementations here with the scikit as compared to TensorFlow. Maximum iterations, and the warm start simply says, well, that we do and can retrain the model, which is the default with TensorFlow Keras sequential model, but not here. And I do some simple random fitting so that the model is fitted, and afterwards I can use partial fit, a little bit of a different approach. The act method is the same when you recall it, right? And the replay is also basically the same here, and there we might see minor differences with regard to the syntax that needs to be used with the one or the other. So for example, here we have this partial fit. This is related to warm start, so we don't reinitiate it when we do some training or replay here, right? Some learning. And the partial fit is that we simply say, well, this is not like the traditional supervised learning. We have all the features, we have all the labels in the training data set. When we do one step, here we want to do it incrementally, and this is what partial fit is. Apart from that, there's not that much of a difference, right? The rest seems to be basically the same. We just have replaced the core, and by core I mean the here the representation. In general, the optimal action policy cannot be specified in closed form, so we need something else, right? So we have approximate representations, and what we use are neural networks in general. So for very simple cases, we could think in terms of some table or whatnot, but here we have the neural network. We can start with TensorFlow Keras, and now we have scikit-learn MLP regressor. So that's the basic change here. And now when we see this in action, it's pretty long here, right? Did I execute everything? It's so long. No, there's one thing missing. So 1500 episodes. And here I changed the base parameters from the class definition to 2 and 128. Finished true. This is with regard to the definition of success. when you reach an average of 195 or above with regard to carb pool, then this is supposed to be a success. And we run it now for a maximum of 1500. So if it reaches an average, as pointed out, of 195 or higher, then it stops the whole thing in this context. Yeah, that's what we have covered previously, right? So here, just a test, a visualization. Once this is done, this is now going pretty slow. I had some other results, and we don't need to wait it out. I just wanted to use this as a, again, as a refresher and a recap. The promise that we now move towards the finance world. So today I'm not going too deep. The only goal that I have today with what I'm going to introduce now is that we have available, that we build a finance environment which behaves exactly like the OpenAI Gym card pool environment. And I want to keep this with regard to the interface absolutely on the same level. So we will have, when you recall it, we have 4 different parameters that describe the world in card pool, and I will work with 4 parameters describing the financial market, the financial world. And I only allow for 2 actions, meaning for the card pool, it was like push it to the left, push it to the right. And here it is simply to go long and short. I'm not really implementing long and short. I simply have this as a prediction game, saying, well, the agent, the bot, shall learn to predict whether the market goes up or down. But this is, of course, easily related then and transferred into some trading setup where I say, well, if the prediction is upwards, then I would go long, and otherwise I would go short. I mean, this is kind of like pretty simple and straightforward. So here in the beginning, standard imports, and I now get back to my TensorFlow Keras world. This would work, of course, with the MLP approach that I've shown before. So multi-layer perceptron from scikit-learn. But Keras gives us a bit more flexibility, and we want to get more fancy later on. Here we have it all available, but currently it's and all pretty straightforward. So setting the lock level for Keras to disable eager execution and importing it. So here on this machine I have 2.6.2 installed, and I use only standard stuff. I don't think this was the same as last time. Let me check. I'm not using, no, there is no dropout actually used. So this could of course be used as a to avoid overfitting. But it doesn't hurt, I mean, to introduce it. You know, we have to take care of quite a number of seeds here. So random from Python, NumPy random, TF random, the environment has seed and the action space. So now you might wonder, oh, if we are not using OpenAI Gym, yeah, but I said what I want to build, what I want to show is a finance work maybe was also that the training was slowing it down. So I noticed a little bit late actually that this was slowing down. I hope you can hear me and everything is fine. It's quite a bit of stuff going on here with the second display, etc. I was just checking the other notebook. So I was talking about the setup that we have a finance environment which should behave exactly the same way, right? Like duck typing. It's not OpenAI Gym, but it should behave the same way. Now this has finished in between, and you see 408 was kind of like the number. So no 1500 iterations in this context, 3 minutes. 30, and you see this goes kind of like pretty straight up here with the implemented approach. So basically, I would be more satisfied with what I see here with maybe when you recall the variance variability here from Keras, and we see that we get a perfect result here as well. So MLP maybe a bit faster. I found it slow. I don't know when I checked it before. Maybe there was, now it's a little bit too much going on here on the machine with the training, etc. But you see this is kind of like a nice learning curve, if you want to call it like that. And it solved the card pool game perfectly. 100 games with an average total reward 200. So perfect 100 times. But you have it available. You can use Colab. You can download it and try it yourself, right? This is all now at your fingertips. Excellent. Sound seems to be back. Somehow the machine froze for whatever reason. Again, too many things. I said that's almost as fast as back home, but the Mac Mini with the M1 seems to be a bit more powerful to do all these things. Yeah, getting back now to the finance story. The setup should be now well known. We've seen this before with card pool and Q-learning. The agent is the same. So this is my idea, right? You have this like with AlphaZero, and with AlphaZero, they started before with the AlphaGo versions, and they have had different iterations. AlphaGo ABC, but they use the name, right? Sedol, etc. And then they move towards AlphaZero, and AlphaZero now saying, well, this is not only for Go. AlphaZero can also play chess and shogi. And this is a little bit the idea. Of course, we are here on a completely different level as compared to chess or the game of Go, right? This is for sure something else. But still, we have the same deep Q-learning agent, right, that we can walk through again rather quickly. Gamma, hidden units, optimizers, the learning rate is fixed, and this double under init method, right, is as before. So even when we had like MLP, this looked basically the same. So there was the idea as simply replace the heart of the operation, if you like, the core. But now we are getting back to the Keras world sequential model, just 2 hidden layers. So here I'm not allowing for more hidden layers or less hidden layers. I fixed it too. The only thing that I allow here is the number of hidden units. By default, we had, what do we have? 24, right? 24. And the rest basically is the same, right? Here we have the act method, looks the same, right? We have the replay. And you see here, that's what the one difference that I highlighted before with scikit-learn, the MLP regressor. We have this partial fit, right, to do the incremental fitting. Here, this is simply by default that we can do the this partial fit, right, if you want to call it that way, because we work here just with a single state action reward pair, right, not pair, triple in this context. Right, so this is by default the same whether we have some supervised learning where we have, I don't know, 10,000 feature and label rows, or just one here, right? One set of features and one label only. So I pointed out in the previous webinar that this is what makes it kind of slow, this incremental training, because of course when you do this for 10,000 at the same time is something else than when you do it 10,000 times sequentially, right? But again, it's the same agent that we had before. Maybe here and there might be some numbers change. The learning is the same, the output is the same, right? Here with regard to finish, this is still what is from before, but here there won't be any finish because in this setup now, when we applied the same DQL agent now to the finance environment, then 195 has no meaning. So I explain what kind of like the goal is in this context. So I will turn this off, but I left it in just to illustrate that's indeed the same agent. And here, yeah, we have the testing where we say, well, now let's check with the optimal policy only, no exploration anymore, just exploitation of our optimal policy represented as the deep neural network, and nothing else in this context. So after this intro, let me see again. I didn't execute that line, but now everything should be executed. The finance environment. So what do I do here? There is the observation space, which I have shown as a class, embedded class of the OpenAI Gym environment. And here I simply mimic what I've shown before. So the only thing that I give back here is the shape, and that's kind of N, the observation space. So this is 4, right? You recall box 4 and 2 actions, 4 and 2. These are the 2 major numbers. The action space now, we have a seed for the action space, and we have a sample method, and we also have the number of actions. So it's a has 2 more methods, but this is just like to mimic exactly the API, so that the agent, which I haven't changed, is able to interact now with a finance environment, right? And now we get to the finance environment. Let's have a closer look here. So I work with some data set now. It's historical data, which is available on my server. Maybe I can show you this, because otherwise you might wonder. Many of you have followed my program, for example, know this. Let me see, I should be in the right. Yeah. This takes always a bit here with Jupyter Lab. When I open this here in Jupyter Lab, I see the CSV representation. Here's a nicely formatted table. The first column is the dates column. Then I have up here the headers, date, Apple, Microsoft, Intel, Amazon, Goldman Sachs, SPY, SPX, WIX, US dollar, gold, and 2 gold ETFs. And this is a time series which starts at the beginning of 2010 and goes until the end of 2019, 10 years. So here is like the first day of 2020. And you see it's kind of incomplete here, but we are only going to work with single columns anyways, and there might be some drop and aid during the import. But basically end of day closing prices for some, I don't know, 12 names, 12 instruments. Here's from Refinitiv, so RIX, right, as instrument code is what you see there. And this is what I'm going to use as a fixed data set. So this is of course completely simplified in this context. So I need to pass in a symbol and I can define features. And here I keep it pretty simple, but I nevertheless have, let's say, one option, namely between the price level or returns that I can use as features. Observation space, can imagine we now go with 4 as before with Carpool, action space 2, and I now define here a break condition in the form of a minimum accuracy. So I say, well, if the accuracy of the agent for one episode drops below 74.5%, then the agent lost the game. Like with Carpool, right? There are certain conditions, physical in nature, right, which says, well, you lost, the poll dropped. Not successful. And this is what I want to mimic here, and I measure the accuracy. I give the agent a grace period, right? If you have the first 2 incorrect, right, you're at 0%. So we need to wait for, I don't know, 15, 20, 10 minimum, and then calculate the minimum accuracy, right? So that's the idea here. The data is retrieved that I've shown you before, and from the data I extract the log returns. And my labels, it's like the action, the prediction, here is simply the direction of the market. And the market is then one instrument that I pick from the data set. So get state returns the current state. So we can think of it, we have like a fixed window, like the data set fixes it, start and end, right? And then we move 4 price points a time forward, like a rolling window. Everybody who uses Panda's rolling window, right? Like rolling mean, let's say. That's the same idea. We have this rolling window where we start with the first 4 and then the next 4 and then the next 4, but rolling. We step forward here, end of day data, 1 day, another day, but always 4 lags, if you like, are used. And the lags can be price or the lags can be returns. So here I provide the state, the next state, the next state, the next state. See it here is simply a pass. There's nothing set. And here is the reset method. You recall with the OpenAI Gym environment, we had this reset method. There was some randomness included, right? The pole position and the card position was not always the same. There was some randomness included. Here we don't have any randomness yet. Later on, we might include something like this, but the total reward is set to 0, accuracy is set to 0. Here I start at a certain bar, right? And I need a minimum value, like if I have 4 lags in analogy to the card pool, then I go with 4. And what is now a step? I take an action, right? And here it is checked whether the action is correct in terms of like, again, it's not really an action, it's more like a prediction game, if you like, right? The agent shall predict whether the market goes up or down. Up is a 1, down is a 0. And if it is correct, then there is a reward of 1. If it is not correct, there is a reward of 0. So pretty simple, like with card pull, just a +1, or I mean, with card pull, when you lose, you die immediately, so to say. We calculate the total reward, we move the bar 1 forward, and we calculate the accuracy here, right? So then we have a couple of break conditions. When we reach the end of the data set, well, we are done, right? You could consider this a success. It is considered to be a success, like with the 200, right? When we have a data set with 1,000 data points and I reach the final point and I haven't broken any of the other conditions here, like the accuracy dropped below 47.5% or whatnot, then yeah, I'm successful, right? But nevertheless, the game ends at the end of the data. Whenever I have a success or a reward of 1, I'm not done. I can do another prediction. If I'm wrong and the accuracy is below my threshold, right, and I'm like 14, also 10 bars in, then I'm also done. And there might be some leftover cases which are set to false. Get the state info, also to mimic exactly the API, simply an empty dictionary, and I return state, reward, done, and info. So this is something that you should recall from the carpool environment. These are the 4 elements that we get there. So just looking here for a question. I told you when I look to my left hand side, there's a question with regard to AlphaZero, AlphaGo for trading. Yeah, no worry. I shouldn't worry about the answer. I was thinking, I once pointed out that Google, with all the technology, they should be able to come up with like the at least artificial financial intelligence, something like a superhuman financial intelligence, and to make gazillions of money. And I think it was on a panel and somebody pointed out that Google can make more money with the stuff that they do, and instead of like going to the markets and try to trade. I'm not sure about that. I think with what they have come up with, if they would put the power in the brain, so the brain power, the compute power, and the algorithmic power behind trading, I think there would be something in it. And if they do it, or if they test it, check it, or I don't know, they probably don't talk about it. I'm not sure, but I think it would be something that can be kind of straightforwardly, I don't know if easily, but straightforwardly adjusted to accommodate like a financial environment. You just need to get the API correct, but this shouldn't be the biggest deal, in particular not for a company like Google or DeepMind. Yeah, speaking of finance environment, we now have our finance environment together. So this is not the most sophisticated one, but it's also not that long, right? We don't have that much code here, but nevertheless, it behaves, hopefully, the same way as our OpenAI Gym environment. So yeah, let's see how it behaves. I'm just talking about it abstractly, but we can check it here. I instantiate the environment, and maybe let me get started here with euro US dollar as the feature. So I set up here symbol and feature. So this is plural, but it refers to like the 4 legs, right? I can change between price and return, but always I'm going to deal with 4, like here, the observation space 4. This is what I'm going to deal with. So let's get started with the instantiation. Now, given the code, the setup, the data file that I've downloaded here manually is retrieved in the backend, and some data preparation has been done. And when I do and reset here, you see that I get now the output. I get 4 different prices, right? It's interesting. No, I just wanted to say where we're coming from, but what I am doing here, so I didn't emphasize this, I normalize the data set here throughout, right? So I don't work with the regular outputs. I normalize the data set that I return, right? So the whole, if you like, the whole data set is normalized, and we know, kind of like that's a stylized fact, that neural networks work much better when you have Gaussian normalization or Z-score normalization is used here. So these are not the real exchange rate values, right? This is something normalized. So I can sample here from the action space. This looks and behaves the same as with the card pool environment. So when I do this a bunch of times, I only get zeros and ones randomly chosen. And when I now have such a random action, let's say 1, and again, action, we are still like at the transition in terms of it's not really an action, it's a prediction game, right? More like a quiz, right? Dear bot, what do you think? You see like these 4 prices, normalized prices. What do you think? Will the market go up or down? So that's the idea here. And again, the then transition to some trading setup, going long or short, is not a difficult one. So I take the action, I do the prediction, and what is happening, I get here the next step, right? So the whole thing is moved 1 step, 1 bar internally forward. Here is a +1, there's a false, and see it here, so a bool, an integer, a bool, and an empty dictionary. That's basically the structure. And now comes the time of our card pool agent, the DQL agent here. I set gamma to 0.5. I comment on that. And Keras optimizes RMS prop. We can try it with Adam as well. And let's get started. So I hope that the machine is not now freezing again. So just checking for some questions. I said we have the chat on Discord, but they're still, right? Yeah, there's a question. What are the 4 features? It's basically qualitatively just 1 feature. It's the price, the normalized price, but these are 4 legs. But this is just like we provide a view on the market for the agent of 4 legs at a time. So if we are today, or let's assume we have Thursday night, like today is Thursday, and let's assume we have Thursday night, market has closed, then we provide the agent with 4 numbers, the closing price today, yesterday, Tuesday, and Monday. And the game is now for the agent to predict tomorrow's market direction, whether the market tomorrow, given these 4 prices, goes up or down, right? And translated to investing, you would say, well, if my prediction is up, I would go long. If it is short, I would. If it is down, I would short. So here we have now 300 episodes, not too many. The final total reward is 2511, and indeed the data set has a length of 2511 data points that are used here. So meaning that indeed the maximum was reached here for the agent, in that the agent reached the very end of the data set. So the average, on the other hand, is just like 750, but we know epsilon here is an important factor, and we see that still some 22% of the actions are exploration, so are simply randomly taken. I mean, this is like when you would have an algorithmic trading program, or an algorithmic not a trader, some trading bot, and you would say, well, 25% of the time choose some random position, probably not the best thing to do, but we can still go and test it. And what is about testing? Testing now means, as we recall, that we completely exclude exploration. It's just exploitation. And we see here the results. Oh, it's like mixed, it's going up kind of quickly. All these values are averages, and this is like the cubic regression for the averages, and then it goes up again. So we can give it 300 more iterations. So this will be a warm start. So it doesn't start from scratch. It starts where it finished with the neural net, and now it trains like font. But what we now need to take into account is that the agent is trained over and over on the very same data set. So there's already the one major difference to the card pool environment. For the card pool environment, every reset gives a different starting point, right? That's different here. So we always have the same starting point. We have like a fixed data set, and we simply repeat the game and the game and the game, right? This is like, I don't know, playing a game of, or trying to solve a labyrinth game, right? We say the labyrinth is fixed. It's maybe more interesting to train an AI agent on a setup where the labyrinth changes all the time, and the agent learns general strategies. But this is not where we are yet, right? We will get to that. Here it is simply like one thing, and we expect the agent first as a starting point to solve the one thing based on the fixed data. Of course, I could then replace it with another data set, etc., right? Here it's just the one data set, which is euro, US dollar in this case. And you see the agent improves, so the averages now climb. So slowly but surely, obviously. So exploration just 5%. Oh, this is on the test data set. That's pretty bad. But here now towards the end, it improved quite a bit. But I can tell you already that this is to a large extent due to the fact that we are working with price data. Sorry, I want to just iterate this once more. On price data and not on returns data, right? So let me quickly check here. There's something. Okay, no. There have been some posts. Okay, but not questions in this context. Yeah, there's another question with regard to the features. Typical question: why can't we provide different features here, such as indicators? This will be one of the next steps. So to feed the agent, the trading bot, with typical financial features like indicators. Let's say something as simple as a simple moving average, or some momentum values indicators, or some related to volatility or RSI or Bollinger Bands or whatever you might come up with. Of course, this can be added, and this will be added. You see here, this is QLearnFin_1. And in one of the next notebooks, we will add more meat to it in terms of giving it different features in this context. But here, again, I wanted to keep it as simple as possible, and this means for us exactly the same way, exactly the same setup that we have had for the card pool game. right? So while this is still working, so towards the end, it's now slowing down a bit. One of the major changes that I can do here is, instead of like the price as feature, I can also now go with R. So log return as feature. So this is still running. Let's see. We are closing in, but you see the average now is it has dropped now again. So this won't be that good. So we don't need to wait this out here. Therefore, let me now reinitialize this environment here. So now we see that we have returns, normalized returns, meaning that we now have negative values and positive values, obviously, not only due to the normalization, but from the outset, right? We have negative and positive returns, so the data set is different, and usually you would train a machine learning algorithm or a neural network, a deep learning algorithm anyways on returns instead of price data. So this now has different numbers, but it works exactly the same way, right? I said before, there's one major difference. So it always starts with the same first values. So when I do reset here, it gives me always the same thing. So there is no randomness. That's a difference to the card pool environment. And I said, I comment on this, that gamma is now set to just 0.5. And why do I do this? So let me maybe simply So let me maybe simply start this so that we can use the time in between. Yeah, why do I set this to a half? Yeah, in Q learning, the basic idea, I emphasized this before, is that we not only take into account the current immediate reward, but also the future delayed reward. We discount it, admittedly, right? It's not on the same level as immediate reward in general, but nevertheless, we include it. And the idea is that in many circumstances where Q-learning agents are so good, like chess and Go, right? It's not only important what your current move, let's think in terms of chess. For me, it's much easier because I pointed this out, I've now played Go. For chess, when you make a chess move, it's not about this very move, right? It's about positioning and strategy and control of the center and attack lines, etc. So there is much more stuff involved, which is important later, right? So you're not only concerned with like the very next move, but rather with like moves going forward. And therefore, you need to take into account like the future delayed reward, which you discount. This assumes that you have influence on the future, but here with our simple setup where we have some fixed data set, the agent doesn't influence the future. So that's another problem, I would say, in the analogy here. Technically, the finance environment behaves in the same way, but we have a fixed data set. So the agent, no matter what the agent does, like 1,000 times up, 1,000 times down as a prediction, it doesn't change the data set, right? And therefore, the delayed reward is, to be honest, here, not really important. Only when we later on have a different measure, like accumulating, for example, profits, getting the highest return, for example, right? Then this becomes more prevalent. But still, it lags here. This analogy lags. Technically, is the same, but the analogy that the agent can influence the environment is not given. Right, and now we see that this agent, which was trained 300 episodes, is for 3 iterations perfect, but this is not a surprise. I can do now 30 or 300. If it is perfect on one, it is perfect on all the others, because it is the same data set. With Cardpool, we have different starting points, like the whole game plays out differently every time. Here, it's the same thing. Once I have, once I know the way out of a labyrinth, I know it. If I don't forget it for whatever reason, I can solve it every time. And you see here, the average wasn't kind of like so great. But for the game now, for our static game, it has solved it perfectly. But it's just the one thing, right? Given that we are now working with returns, what can be done? For example, you can have your trained agent, which you let then interact, for example, with another time series from which you derive the returns and then normalize the returns, right? With regard to price series, I don't think that it would make sense, but the returns, and that's the basic idea. If there are patterns in the returns and the agent learns these patterns, maybe, probably, I don't know on which side you are, you can transfer what the agent has learned to some other thing. So meaning that, for example, you train such an agent on, let's say, the Apple stock, and you then let it trade, at least you test it maybe on Microsoft or Meta or whatever you want to do it. But you see here, the same DQL agent which was able to solve the card pull game perfectly. The MLP agent had a better performance and was quicker to train, can be applied, can be deployed here to a finance environment and can learn to trade. Admittedly, it's a pretty simplistic environment, but as we go, we will add more twists, more features, and by features I mean it in general, but also specifically, more narrowly, machine learning, deep learning features to the story, so that we get a more realistic environment. So of course, natural extensions here would be to change the number of lags, right? 4, maybe 8, maybe 12. Maybe I can use price plus return information. Maybe I can use return plus whatever, right? I mentioned a few features before. Indicator 1, 2, 3, 4, 5, 6, 7. This all works. I simply need to adjust or keep it flexible, the structure of the neural network, and then I can do the same trick but with a more realistic environment, and from there I can take it in multiple directions. And one of the other things that need to be added is to make the data set a bit more realistic. So there are a couple of approaches. We can think in terms of Monte Carlo simulation, for example, where we train the agent on, let's say, 1,000 different price paths, for example, to learn about mean reversion or whatever. So these are all topics that I'm planning to cover in later webinars, but we have done the first major step from playing a game to trading in a market and learning to predict the market. And at least in this particular run here, the agent got it perfect. And again, 3 is just for illustration. 1 would have been enough because this is now reproducible over and over again. There wouldn't be any surprise in this context. There's a question. I have used both price and return here. There's a question with regard to why I'm using these. This is just to get started. Yeah, very simple. So although I said before, it's well known, you should use stationary time series data in order to do your regression or your deep neural network training. For example, price is something that most people can relate to in terms of like every day trader does some chart analysis, and people usually, when they look at charts, they look at prices and they hardly ever look at returns, right? Maybe this is a secondary information set that I take into account. But said here, I would usually work with the returns in order to predict the next day's return. So trying to capture potential patterns in the return structure to predict the next movement. This would be the idea. Yeah, more to come in this context. This was my plan for today, to get this through this major step. And there's a technical one. Maybe we can discuss this offline, and I would recommend that we do this in the Discord chat, because the chat here in GoToWebinar simply gets lost, and we cannot keep up the discussion about these technical topics or any other topics to this end after the session has finished. So therefore, would be better to have the chat and the questions all in the Discord chat. So in that sense, let me just do a bit of house cleaning here. Data set downloaded. Maybe I can also push this. It's not that large, this data set. And in that sense, this is what I wanted to show you today. Just a final check with regard to the questions that you might have here. There is a chat channel in the QUANTS dev Discord server, which is supposed to have, and I've also put all the links to GitHub repository, to the Colab link, so to say, to work with the Jupyter notebooks in Colab from the repository. So there is a channel called chat, and this is what is supposed to be the major exchange. All right, in that sense, I wish you happy reinforcement learning for finance now, and maybe you have already quite a bunch of ideas which you want to implement based on the framework that you have available. And that's kind of straightforward. It's not that much work, kind of like to add something else and to adjust it from, I don't know, 4 legs to 8 legs, for example. Yeah, give it a try, play around with it. I think that's the best way to get into this exciting field. In that sense, I see you in the next webinar. Take care. Bye-bye.